Team, welcome to Wiggins Maths. In this video we're going to be looking into the wonderful world of first order differential equations. Now, little heads up, this is the topic that students traditionally find the most challenging within the integration unit. I just want to reassure you, it's not that bad. You will be fine, you just need a little bit of practice. It looks a little bit awkward, but you just need to go for it. As always, do not neglect the formula booklet, could be really useful. Okay, so this is what a first order differential equation actually looks like. Okay, so we've got a first derivative, hence first order, and it's equal to a function of x multiplied by a function of y. Now, to solve a differential equation means to find out what the general solution is. So in essence, it could be in the form y equals f of x, just like our traditional integration so far. Now, a general solution is where we have plus c, or our constant of integration. A particular solution is where we actually find out what that constant is using what we call a boundary condition, something like when x equals 1, y equals 2. So there are three steps generally of how to do this. Separate the variables, all the y's on one side, all the x's on the other. Step 2 is to actually then integrate both sides. And then our third step is to use some form of boundary condition if we have been given it. So let's go for it. First order differential equation, function of x multiplied by function of y. Let's separate the variables. Now, a little hint here, take as little over to the other side as you possibly can. So I'm going to leave the 6 on this side. So let's go for it. So that will be y to the power of negative 2 equals 6x dx. Okay, so we separated the variables. Step 2 was to integrate both sides. So y to the power of negative 2 with respect to y would be negative 1 over y, or negative 1y to the negative 1. Integrate 6x with respect to x would be 3x squared plus our constant. Okay, it's not quite in a useful form just yet, so I'm going to try and write this in the form y equals f of x. So I need to take the negative reciprocal of both sides. So let's do that. Okay, I'm not happy with my constant here. A constant is just a constant, so we don't need it to be a complicated term. So I'm going to rewrite what that constant is. Okay, I've have to use a different variable because I can't use c. And then it's in the form y equals f of x, so not too bad. Okay, so second example looks a little bit more complicated. It's really, really not. Let's separate the variables. Done. Integrate both sides. So when I integrate this side, I get y squared subtract 4y. And when I integrate this side, I get that. Now, this is fine. This is absolutely valid. It's really, really, really awkward to write this in the form y equals f of x. You know, this is absolutely true. So don't panic if you've got yourself in this form. That's fine. Unless the question said, write it in this form, this is absolutely valid. Okay, so this one looks a little bit more complicated again. So separate the variables. We know that square roots tend to be almost like the enemy, so we can write it as a power of a half instead. Okay, so let's then integrate. So this side, nice and simple, becomes ln y. This side, okay, I'm going to have to do a little bit of work here. So I'm going to rewrite this initially as that. And then hopefully we can see that actually when we differentiate this, we get this. So using that reverse chain rule idea. So actually what we end up with is 1 plus x squared to the power of a half plus c. Okay, if I was using the reverse chain rule. Now, ln y equals this. It could say write your answer in the form ln y equals f of x. Or it could say leave your answer in the form y equals f of x. So I'm just going to show you how to write this as y equals f of x. So I'm going to have to take exponentials of both sides. So that will become y on this side. And then on this side, the horrible looking this. Again, not happy with my constant up here. So what we need to remember are the things we did at GCSE, so index laws. So when do we add powers together? Well, it's when we multiplied things with the same base together. So actually I can write this like this. Okay, now e to the c is just a constant. So actually I'm going to rewrite this. And we tend to use capital A on a question of this type. So it's capital A lots of this thing. And that's it. That's about as complicated as it gets for this. Okay, so rewriting that constant as capital A. Okay, fourth example. Again, involves exponentials. It doesn't matter. We know what we're doing. Separate the variables. Let's integrate both sides. Okay, again, the question could be e to the y equals f of x. It could be y equals f of x. So let's just have a look at how to make this y equals. We're going to have to take natural logs of both sides. Okay, now this is absolutely fine. Okay, we could be given a boundary condition to work out what c is, but this is an absolutely fine way of leaving it. Okay, so our final example of a general solution. Now this looks a lot trickier, okay, and in reality, again, it's not that bad. Remember, to solve a first order differential equation, we want a function of x multiplied by a function of y. So let's try and make this happen. Index laws. That's definitely true. Okay, we want these to be two things multiplied together. We can take out a common factor of x, and then we've got it. So I've rewritten the initial problem. Now we're going to separate the variables. I'm going to write it straight away as e to the negative x. Divide through by e to the x. It becomes e to the negative x. Right, okay, so what are we going to do here? Well, we have to integrate both sides. And this obviously becomes the trickiest bit the more complicated the function becomes. We've got a lot more to do here. So let's integrate this left-hand side first. I recognize that the denominator differentiates to make the numerator. So, using one of those techniques that we have looked at throughout this unit. And then this side, well, I'm pretty confident that this looks like integration by parts. It's two functions multiplied together. You differentiate this and it becomes more simple, and we can integrate this. So let's do this. And what's really important in this is to not try and take shortcuts. Shortcuts lead to mistakes. Okay, so UV, subtract the integral of v du, so that's a negative there, so I can change this to an add. So natural log of 2 plus e to the y equals negative x, e to the negative x, subtract e to the negative x plus c. Whew. We've done it. Okay, now that's okay to leave it like that. Okay, in this question it did say leave your answer in the form ln g of y equals f of x, and we've successfully done that. Okay, so the next couple of examples are particular solutions. We've been given a boundary condition. It can often be given like this or within the text itself. Also in this example, I've made sure I'm not using the variables y and x because that can sometimes be a little bit misleading. So separate the variables. Integrate both sides. Okay. Now it's at this point I tend to use the boundary condition to work out what c is. So let's do that. So r is 2 and theta is 1. Okay, ln1 is 0, so that implies that c must be negative half. So our particular solution is this. Okay, and you know that will do. I mean, it'd be better to write it in the form r equals, which we can also do. You know, we could take the negative reciprocal of both sides. It's a little bit messy, you know. We've got some constraints here. You know, ln theta must not be equal to 1/2. Theta must be positive. You know, things like that. Okay, final particular solution to find. Boundary condition is up here. Separate the variables. Integrate both sides. Okay, this is a bipart situation. So let's do this up here. Again, if we try and take shortcuts, we'll go wrong. Lovely. So uv, subtract the integral of v du, negative, so we can add. Okay, so we've successfully integrated. Now we're going to use the boundary condition. It was when y is 1, x is pi over 2. So let's substitute that in. Okay, evaluate all that and we get c is -1, I believe. So our final statement, our particular solution, is that. And that'll do. That's fine to leave it like that. We could take exponentials from both sides, but we're not told to. If we were told to, we can then do it. But that's absolutely fine. Okay, so all that's left to do in the next video, we're going to add some context to this. Okay, we're going to make them into worded problems. But for now, a reminder that watching it doesn't instantly mean you will be able to do it. Practice is going to be really, really important for this topic, as with all the other topics, and the more you practice, the better you'll become. If you found the video useful, make sure you subscribe, tell your peers. I'll be aiming to upload more videos each week to ensure we are as successful as possible. And of course, amateurs call it genius and masters call it practice.